Hello everyone, I'm Zhang Zhaolan from Huazhong University of Science and Technology. Our paper proposes a DAG-based consensus protocol called GradedDAG, which has significantly lower latency than the state-of-the-art. Okay, here is the outline. Let's begin with the background. The consensus protocol is a key ingredient to the distributed system. In a distributed system, a group of independent computers, here we call replicas, should act as a single server that will level fair. This means that when multiple clients send different requests to the system, all correct replicas can reach an agreement on the requests, even there are some faulty replicas. So here all correct replicas will first commit R1 and then commit R2. If the consensus protocol can tolerate Byzantine faulty replicas, it is called Byzantine fault-tolerant consensus, or BFT consensus for short. A classical BFT model consists of n replicas, where n is equal to 3f plus 1. And up to f replicas can be Byzantine faulty. Byzantine faulty replicas can behave arbitrarily to defect from the protocol. In addition, a BFT consensus has to achieve two properties, namely safety and liveness. Safety requires that any two correct replicas commit the same request at the same indexes. And liveness requires that a request proposed by a correct client will eventually be committed by all the correct replicas. Especially, if a BFT consensus can work in asynchronous network, we call it asynchronous BFT consensus. Next, I'm going to introduce a broadcast protocol, asynchronous reliable broadcast, or RBC for short, which has to achieve four properties. First property is consistency, which requires all non-faulty replicas should deliver the same data. Second is validity. It is said that if the broadcaster is non-faulty and the broadcaster data D, each non-faulty replica will eventually deliver D. Okay, the integrity. The integrity requires each non-faulty replica will deliver at most one data. Finally, the totality. The totality requires if a non-faulty replica delivers the data D, all the non-faulty replicas will eventually deliver D. Now that we have a rough understanding of RBC, a very natural question arises. What can RBC be used for? The RBC protocol can be used to build consensus. For example, DAG-based BFT consensus. This consensus is based on directed acyclic graph structure, or DAG for short. Existing DAG-based BFT protocols all operate in successive waves, with each wave containing 3 or 4 RBC rounds to broadcast data. We can see in the picture. Now I'm going to introduce a state-of-the-art DAG-based BFT consensus, task. This will allow us to gain a more detailed understanding of DAG-based BFT consensus. In task, each wave contains 3 RBC rounds to broadcast data. Yeah, we can see. In each wave's first round, task will elect a leader to commit data, as shown in the animation. Although each wave contains only 3 RPC rounds, each RPC round requires at least 3 communication steps. This results in higher latency. Let's see. Not only task. Almost all DAG-based BFT consensus latency is not very satisfactory. Here I give a table to show it more intuitively. We can see in the best case scenario, they need about 10 communication steps to commit a block, and even dozens of communication steps in the worst case scenario. Therefore, a literal question arises. Could we reduce the latency of the DAG-based consensus? So next, I will introduce our protocol, GradedDAG. To reduce the latency of DAG-based consensus, we use consistent broadcast, CPC for short, and graded RPC, gRPC for short, to build our GradedDAG. As shown in the picture, each wave contains 1 gRPC round and 1 CPC round. Our protocol has really low latency. In the best case scenario, it needs 5 communication steps to commit a block, and only 7.5 communication steps in the worst case scenario. Next, I will first introduce CPC and gRPC before introduce GradedDAG. First, CPC. CPC is a weaker broadcaster abstraction than RPC. It do not have the totality property. It cannot ensure that all non-faulty replicas will deliver identical data. But CPC is more cheaper, that it can be implemented through 2 communication steps. Okay, next is gRPC. To reduce the latency of DAG-based protocols, we propose a new protocol called GradedRPC, gRPC for short. gRPC is an adapted version of RPC abstraction, which allows a replica to deliver data with a grade, either 1 or 2, as shown in the animation. Okay, it needs 3 communication steps. gRPC also has 4 properties. The consistency, validity, and integrity is similar to RPC. But gRPC has an additional property, perceptivity. It requires that if a low-faulty replica delivers D2, it can infer that at least 2 F plus 1 replicas have delivered D1 or D2. Let's see. Next, I will introduce GradedDAG in 3 parts. How to build DAG, how to elect a leader, and how to commit blocks. Okay, first, how to build DAG. There are 2 cases. First, in gRPC round, replica needs to wait for 2F plus 1 CPC blocks in last round. and replica should reference all the CBC blocks in its gRPC block and broadcast it. We can see on the picture, in the picture. Second, in CBC round, replica needs to wait for 2F+1 gRPC blocks with grade 2 in last round. And the replica should reference all the gRPC blocks with grade 1 or 2, yes, 1 or 2, in its CBC block and broadcast it. Second, how to elect a leader? We use global perfect coin, we call it GBC for short, to randomly elect leader. In each CBC round, we elect a leader in last gRPC round. Finally, how to commit blocks? Our commit ruler is very simple. After the leader block is refilled by GPC component, each replica will check if the leader block has been delivered with grade 2. If so, the leader block can be committed. But similar to other DAG-based protocols, we will carefully commit all the causal history. When a replica commits a leader block, it first checks if it leads to commit the previous leader block, as shown in the animation. Because of the DAG build ruler we introduced earlier, at least 2F+1 blocks has been delivered with grade 2. We can see. So with probability 2/3, the elected leader block can be committed. Okay. Next, I will introduce two rulers in our protocol. First is safety ruler. In order to permit safety, we should add one safety ruler. After a replica creates a CBC block, it will terminate all gRPC instances whose blocks are not referenced by the CBC block. We can see in the animation. Thanks to the perceptivity property of gRPC, we can get a conclusion. If a leader block can be committed, at least the F+1 long 40 CBC blocks will reference it. So this guarantees a path between all committed leader blocks, which can permit safety. If we remove the safety ruler, some leader blocks which are not referenced by CBC blocks could be committed. This would destroy the safety. Because of the safety ruler, some long 40 replicas may not collect enough gRPC blocks with grade 2. So we add one lifeless ruler. When delivering the data with grade 2 in gRPC, a replica will broadcast a certificate of its delivery. If other replicas receive this certificate, they will deliver the corresponding block with grade 2 as well. So All replicas can get 11 blocks with grade 2, which can permit the liveness. Okay, next I will introduce the evaluation. To evaluate our design, we implement a prototype of GradedDAG and the task in Golang. The configurations are shown in the screen. First, we compare the basic performance between GradedDAG and task. As can be seen from the figure, GradedDAG has higher throughput and lower latency than task. Second, we compare the trade-off between GradedDAG and task, as shown in the figure. GradedDAG delivers a higher throughput than task in the either setting. Okay, finally, we make a conclusion of our work. We identify the issue of high latency in current DAG-based BFT protocols, caused by multiple RPC rounds in each wave and multiple communication steps in each RPC round. We propose an adapted RPC protocol named gRPC, which can help one non-faulty replica to perceive other one's delivery. We devised GradedDAG, a novel DAG-based protocol based on gRPC and CPC, which has significantly lower latency than the state-of-the-art. That's all for the introduction of GradedDAG. Thanks a lot for your attention. Any questions are welcome.